Buoyant force is an important topic in hydrostatics. As long as an object is submerged in a fluid, whether fully or partially submerged, it receives the buoyant force from this fluid. Think about a balloon floating in the air, or a boat in the water. What if the object is submerged in a two-fluid system? In this video, we'll discuss how buoyant force is a result of hydrostatic forces acting on the submerged object, and we'll work on an example problem of two-fluid system. Let's record the hydrostatic force. The hydrostatic force on a submerged surface can be calculated using hydrostatic pressure multiplied by the surface area this pressure acts on. The hydrostatic pressure at a specific location in the fluid, as we previously discussed, is linearly correlated with the depth of this location to the surface. Given by the hydrostatic equation, the hydrostatic pressure equals the product of the specific weight of the fluid, gamma, and the depth in the fluid, h. That being said, if we look at the horizontal direction of an object that is submerged in the water, given the same depth, we have the same hydrostatic pressure and the same hydrostatic force. This applies to all directions horizontally, at all depths. Consequently, the object is at hydrostatic equilibrium horizontally. Now, if we turn to the vertical direction, things are very different. Because the depths are different, we now have different hydrostatic pressures and the different hydrostatic forces. The deeper it goes, the hydrostatic force gets bigger. The downward force, F1, is calculated with pressure multiplied by an area it acts on, delta A. Likewise, for the upward force, F2, as illustrated here, the resultant is calculated using F2 minus F1. When we rearrange this equation, we now see the area delta A multiplied by the difference between the two depths, H2 minus H1. This is actually the volume of the column, delta V. As we integrate this calculation all through this submerged object, the resultant is the buoyant force, an upward force determined by the specific weight of the liquid and the submerged volume of the object. This volume is also often referred to as the volume of the liquid displaced by the submerged object. This is a simple but a very useful equation that has many engineering applications. In a one-fluid system, the calculation of buoyant force is usually straightforward. Here, let's take a look at an example about two-fluid system. We have a rectangular block with a length of 6 meters, width of 3 meters, and height of 3 meters. Its specific gravity is 0.75. The block is submerged in a two-liquid reservoir, where the specific gravities are 1.0 and 1.2 respectively. Referring to the figure, what would be the submerged depth, d? Let's start by analyzing the forces about this rectangular block. It is not difficult to see that the block receives gravitational force, Fg, which can be calculated using the specific weight of the block multiplied by the volume of it. At the same time, the block receives two buoyant forces. One resulted from the upper liquid with a specific gravity of 1.0, and the other from the lower liquid with a specific gravity of 1.2. Along the vertical direction, the block is at hydrostatic equilibrium. Hence, all the forces must cancel out. Next, let's write out the three forces one by one. Let's start with the buoyant force. Fb1 is the product of specific weight of the liquid, gamma 1, and the volume submerged in this liquid, V1. Given the dimensions of this rectangular block, We know the submerged volume is 6 meters times 3 meters times L. And because 6L equals 6 meters in this figure, L is 1 meter. The specific weight of the liquid can be calculated from its specific gravity. Likewise, we can write the buoyant force Fb. The difference is that we do not know the submerged depth at this time. So we set this unknown depth as y for now and carry it into the subsequent calculations. So finally, the gravitational force Fg is calculated using specific weight of the block and the full volume of the block. And now we can conclude the actual values of Fb1 and Fg, while showing Fb with the unknown depth y. We then substitute these forces into the equilibrium equation in the vertical direction. Solving this equation gives y equals 1.042 meters. Now the answer becomes clear. We have d equals the sum of L and y. That is 1 plus 1.042. The depth d is 2.042 meters. If you found this video helpful and want to learn more about civil engineering and professional engineering exams, like and share this video, subscribe to the channel, and comment below with topics you would like me to cover in future videos. Thanks for watching, and I'll see you in the next one.